Thank you. Good afternoon, everyone. Thank you for attendance. We're going to begin this session of nanomaterial application with the first presentation titled Assessment of the Electronic Properties in Zinc oxide, silver, zinc oxide, three-layer thin films deposited by RF spectator. And I wish to remind the speakers they have 15 minutes to present their work. After the presentation, there will be a question and answer session. So please provide that. Can you share your screen with us, please?
Is my screen visible?
Yes.
Okay. Okay. It's not maximized? Is it maximized?
Yes. Can you maximize your screen, please? Thank you.
It is maximized.
Yes, thank you.
So greetings, everyone. Today I will be presenting our recent work on zinc oxide, silver zinc oxide, three-layer thin films that are deposited by radio frequency sputtering, and how these structures can be or can serve as a potential alternative to indium tin oxide in optoelectronic applications. So first, I'll begin with an introduction that includes the motivation behind this work, the problem with the current transparent conductive oxides, specifically indium tin oxide. Then we'll move to the objective and the experimental process. Finally, we'll discuss the findings and then conclude. So transparent conductive oxides, we all know, also known as TCOs, are everywhere in displays, solar cells, LEDs, and sensors as well. And the go-to material has always been indium tin oxide for decades because it offers us excellent transparency and an excellent conductivity. But as we know, indium is rare and is expensive, and it suffers from brittleness that makes it unsuitable for the next generation flexible or wearable devices. So the main motivation here is that can we find a cheaper and more flexible alternative that still performs well optically and electrically? So the significance of zinc oxide here is that it's abundant, it's non-toxic, and also transparent with a wide band gap. And if we introduced a very thin layer of silver, we can drastically enhance the electrical conductivity while also maintaining a reasonable amount of transparency. And what's even more interesting is that when silver forms nanoparticles, it examines a phenomenon called the SPR, the surface plasmon resonance, that it is explained that when electrons on the surface resonate with incoming or incident light that adds an extra optical tunability that indium tin oxide doesn't have. And the objective here is that we develop this tree layer that could be comparable to commercial indium tin oxide and analyze the optical and electrical properties and then understand how plasmonic effects from these silver nanoparticles influence the performance. So the films were deposited via radio frequency magnetron sputtering on glass substrates that were cleaned priorly with acetone, isopropanol, and deionized water. And this step is very critical so we could achieve a good adhesion and the surface would be clean for deposition. The bottom and top layers were sputtered at 120 watts in a mixture of argon and oxygen with a ratio of 66 to 33%, with a Moorfield Minilab 060. And the silver interlayer was deposited in pure argon, and then after deposition, the film was annealed at 300 degrees for 30 minutes to encourage silver to agglomerate into nanoparticles inside the zinc oxide matrix, which we expected to enhance both the plasmonic and electrical behavior. So as we can see here, the final structure consisted of 50 nanometers of zinc oxide, 8 nanometers silver layer, and another 50 nanometers zinc oxide on top. This thickness combination was optimized to balance the transparency conductivity. And if the silver layer was too thick, it could reduce transparency, and if it is too thin, it could reduce conductivity. So it's like one side is at the expense of the other. And the plasmonic mechanism is what makes this structure special because it is not a defect, it is a design feature that allows us to fine-tune which wavelengths the film interacts with, which is something that could be used in smart windows or photodetectors. Now, if we look at the absorbance spectra, we can see that indium tin oxide, as expected, absorbs strongly in the UV region and then remains nearly transparent in the visible and the near-infrared ranges. Our three-layer film, on the other hand, also shows strong UV absorption, which is typical for zinc oxide, but we observe also a broad visible absorption peak around 580 nanometers to 600 nanometers due to the surface plasma resonance. That confirms that silver nanoparticles were indeed formed during the annealing. And although this means that the film is less transparent, as we can see, than indium tin oxide, it still opens the door to tunable optical responses. So if we move to transmittance, indium tin oxide maintains a high transparency of about 80% to 33% in the visible range. And the three-layer film drops to around 43% at 550 nanometers with a noticeable dip near 600 nanometers, again due to the SPR effect. But here's the interesting part. Beyond 700 nanometers, you can see that in the near-infrared region, the transparency rises again. So while the optical performance is not yet on par with indium tin oxide, it's still highly tunable. That if we refine the nanoparticle size or optimize the annealing duration, we can recover much of that lost transparency while keeping conductivity high. Now, if we look at the electrical performance, we can see that the sheet resistance of the three-layer film is pretty much close to indium tin oxide, which is a very strong result. The carrier concentration in zinc oxide, silver zinc oxide three-layer is about 3 times higher than in indium tin oxide. That indicates the electron injection from silver. But mobility, as we can see, is lower, which is roughly 2.7 compared to indium tin oxide 33, due to electron scattering at the interfaces. Still, the high carrier density compensates for this lower mobility, and the result is comparable conductivity. And to quantify the overall performance, we use the figure of merit, and we can see that the three layers slightly surpassed indium tin oxide. Even though the film isn't as transparent, it compensates through superior charge transport. And the estimated band gaps using top plots for the three layer 3.8 compared to 3.74 electron volts for indium tin oxide. The slight widening is also likely due to quantum confinement from the nanoscale silver nanoparticles and improved crystallinity after annealing. So in simpler terms, the film absorbs slightly higher energy light, making it more stable against UV degradation. So all these results together means that we achieved a balanced trade-off between transparency and conductivity, which is not perfect yet, but it is quite promising. And the plasmonic behavior is both a challenge and opportunity, which reduces visible transparency, but also adds a new tunable function if we're talking about optical properties. So to bring all of this together, the three-layer film clearly achieved a good balance between transparency conductivity and the plasmonic absorption is an opportunity as well as a challenge because it reduces transparency compared to indium tin oxide. And electrically, the films remain competitive thanks to the high carrier concentration caused by the silver nanoparticle formation. And with a few structural organ optimization, such as reducing the silver interlayer thickness slightly below 8 nanometers or adjusting, let's say, the annealing temperature or time for better control over nanoparticle size, or possibly introducing a buffer layer to smooth interfaces, we could improve both the optical clarity and or the charge support transport. So for future work, we plan to conduct X-ray diffraction, of course, and scanning electron microscopy analysis to observe nanoparticle formation and correlate these morphological changes to the performance. And a systematic study also varying the temperature can help us find the ideal conditions for plasmonic control and transparency improvement, and also varying the thicknesses, as I mentioned earlier, that could allow us also to fine-tune conductivity and transparency. Thank you for your attention.
Thank you, Rafaela, for your presentation. We have time for some questions. So let's say if one have a question. Sorry. Yeah, I have a question, Rafaela.
Sorry?
From the chat. He has a question.
There is one question.
You must have the camera turned on.
Okay. Can you start out your camera, Rafaela, please?
Ah, yes, yes.
Okay, I have a question. With your experience using sputtering technique, which parameter do you think are the more important to improve the optical properties of the position of the tilt films?
I think it would be probably the thickness.
Thickness is the more important.
Yeah, the thickness plays a huge role.
So how you can control the thickness in the sputtering technique?
How can I explain?
How do you can control the thickness of the film in the sputtering technique? What parameter do you need control? I don't know the pressure.
Sorry. We have to monitor. We have to monitor through the deposition. We have to monitor through ellipsometry or profilometry. Monitor the thickness of the film while in the deposition.
Okay. Any question? What is this?
Hi.
Hello, Jorge Cruz. Can you hear me?
Sí, sure. Robaida, in some application of TCOs, the work function is very important. I think you could manage these other parameters and improve your work. What do you think?
You said, sorry, could you repeat?
The work function, did you don't include work function in your electrical properties? Work function is very important in some application. For example, solar cells. I think you should include work function in your properties.
Include what? Sorry, could you include what exactly?
The work function.
Good point, yes.
Yeah, check about it. It's very important in some applications.
Yes, yes. Thank you very much.
Okay.
So there are no more questions at this moment. So thank you, Rafaela, for your presentation.
Thank you.
Do you have another lecture, right? Rafaela, do you have another lecture?
Yes, I have another presentation.
Okay. Can you
Do
share
I do it?
your screen, please?
Okay. Do I start right away?
Yes. So please maximize your screen.
Yes, I maximize.
So, right.
Okay, so
And the next lecture is a structural and optical characterization of gold being oxide, deep field deposited by TCS sputtering and glass techniques. So, Rafaela, please go ahead.
yes. Okay, so this time I'll be presenting how gold-doped tin oxide thin films behave when their structure or optical properties are modified by changing the deposition angle during sputtering. So we'll start with the introduction as usual, motivation, followed with the objectives of the study. Then we'll go through with the experimental details, the characterization methods. After that, we'll move to the results and discussion section, and then we'll finish with the comparative analysis and concluding remarks, as well as future work. So as we mentioned even earlier, thin films are the core of modern optoelectronic devices used in solar cells, transparent electrodes, gas sensors, and photodetectors even, among many others. And in this work, we focused specifically on tin dioxide, which is a wide bandgap semiconductor with a gap around 3.6 electron volts. It is a transparent, chemically stable, and has good electrical properties, which make it a great candidate to implement it in transparent conductive oxide applications. But even though it has many advantages, uh, it has two main limitations that are worthy to mention, which is low carrier mobility and the wake absorption in the visible region. And if we want to overcome these drawbacks, we introduced gold nanoparticles into the tin oxide matrix because gold is particularly interesting. Just as silver, it offers us localized surface plasma on resonance, and that enhances both absorption and scattering and allowing the film to interact more effectively with light. And if we combine it with the DC sputtering and the glancing angle deposition technique, we can control the film morphology by adjusting the deposition angle. So the main objective of this work is to investigate the influence of deposition angle on the structural and optical properties of gold-doped tin oxide thin films. And we want to study the effect of the two deposition angles that we chose, which is the 0-degree angle called normal and 80-degree angle, which is called oblique, on the resulting film properties, as well as analyze transmittance, absorbance, and bandgap variation as a function of morphology, and correlate these optical responses with structural changes that are confirmed by X-ray diffraction. And through this work, we want to show that deposition geometry can act as a simple and effective tuning parameter for optimizing plasmonic thin films. So the thin films were deposited on glass substrates using a DC magnetron sputtering device equipped with the GLAD configuration that allows us to change the angle. We used high purity tin and high purity gold targets with base pressure around 10 with a power of -5 Pascal, and the current density was 50 amperes per meter square. The deposition time was set to 30 minutes, given film thicknesses of about 100 nanometers for 0 degrees and 80 nanometers for 80 degrees. And to analyze them, we used UV visible spectrophotometer nanometry to measure transmittance and absorbance, and X-ray diffraction to identify the crystalline phases and confirm the incorporation of gold. And the band gaps were estimated by the tau plots by extrapolating the linear region. So as you can see here, this figure shows you the two geometries. At 0 degrees, the incoming particles strike the substrate perpendicularly. That forms a dense compact layer. On the other hand, the oblique film, the atoms arrive at an oblique angle that leads to self-shadowing and the formation of tilted columnar nanostructures. And these columnar films are more porous and have high surface roughness, which plays a major role in scattering and the absorption of light. Here we can see the transmittance spectra for both deposition angles, where the planar film exhibits about 48 transmittance at 550 nanometers, and the oblique film shows around 30% at the same wavelength. And we can see a noticeable dip around 550 nanometers to 600 nanometers, corresponding to the plasmon resonance of gold. The deeper dip for the oblique film indicates a very strong LSPR activity and enhanced scattering because of its porous morphology. And interestingly, in the near-infrared region, we're talking about above 800 nanometers, the film regains transmittance that reflects lower optical density and higher porosity. So the absorbance spectra, of course, complements the transmittance, where the film at 0 degrees absorbs about 50% at 550, and the oblique shows roughly 65% near 600 nanometers with a slight redshift. And the stronger absorption is related, as we mentioned, to the plasmonic coupling and the morphological roughness, which is introduced by the oblique deposition. So the GLAD technique here enhances the light-matter interaction by increasing the scattering paths, and that results in greater visible absorption. And that is a property that can be useful, of course, for optical sensors. Now let's look at the X-ray diffraction patterns that we see that they show peak characteristics of tetragonal tin oxide at 26.5 degrees, 34 degrees, and 51.5 degrees that correspond to the 100, 101, and 211 planes. We also see distinct peaks at 38.1 degrees, 44.5 degrees, and 64.7 degrees that belong to the metallic gold. 111 and 200 and 220 planes, respectively. Now, the strong 111 reflection confirms the formation of gold nanoparticles. And in the 80-degree film, the peaks are broader and very less intense, that indicate smaller crystallets and increased microstrain that are consistent with the columnar structure. And these structural features directly explain the optical behavior that we observed earlier. And here to summarize and compare, the oblique film exhibits a very strong absorption, which is stronger than the normal film, and a slightly higher band gap, a result of enhanced plasmonic effects. And the correlation between X-ray diffraction and optical results confirms that microstructural evolution with angle strongly impacts our optical performance. So if we want to summarize it, we can say that by varying the deposition geometry, we can tune both the transparency and absorption. And to conclude, we can say that the deposition angle definitely influences the structural and optical properties. The 80-degree film exhibits enhanced plasmonic absorption, a higher near-infrared transmittance, and a slightly larger band gap. And the analysis of the X-ray diffraction confirms the coexistence of the tin oxide and metallic gold phases together with microstructural anisotropy due to the oblique deposition. So for future work, of course, we plan to perform SEM as well to directly visualize the surface morphology and the columnar nanostructures and measure porosity. And also, we'd like to conduct electrical measurements such as resistivity and carrier mobility to link these properties with electronic properties as well. And finally, we aim to integrate these layers into plasma-enhanced solar cells or even gas or optical sensors to evaluate the potential.
Does anyone have a question? Virtual audience may also ask questions too. One. Okay, Rafael, I have one question. What limitation are there using combination of two techniques like sputtering and clad techniques in terms of the stability, reproducibility, and uniformity of the position of the thin films?
I think DC, if we're comparing with radio frequency, I think DC is a good method if we want to deposit conductor materials. They are stable, of course, but I think radio frequency is better if we have insulating materials such as zinc oxide, such as that. But I think in terms of conductors, or in our case tin and gold, it is very stable. It is a good method.
Okay, thank you. So there are one more question for the moment. So we thank to Rafaela for her presentation. So the next lecture is the structural properties of gallium nitride thin fields brought by RF sputtering. Presented by Jorge Cruz Gomez.
Hi everyone, I can share.
Yes, please.
Okay.
So can you share your screen, Jorge, please?
I can do it.
What is the trouble?
I click but if this doesn't, I can't.
Jorge, can you send our presentation for email?
I can do it. It's
Send
not
an email. Send an email with your file.
Yes, I
So the solution is, please, you share your file with us, and you can put your slide on. In the case that you can share your screen.
I sent you the presentation.
Let me check, please.
Okay. I don't know why not. I can share.
Could you check the chat, please? I send you the email address for you to send the slides, please.
Okay, let me. Okay. I sent it.
Yeah. Okay, can you see your presentation now?
Sure. Yes, I can. Okay. I can start.
Yes, please.
Okay. My name is Jorge Cruz, and I'm going to present this work. The presentation is structural properties of gallium nitride in films run by radio frequency sputtering. And next, please. The next slide, please.
Let me just second.
Okay. Gallium nitride is a material with interesting properties. So is very a lot of investigation. I think that this is the material for the next generation for power of optoelectronic devices. So it's very important to study it. And the next, please. Some interesting properties about the gallium nitride are this semiconductor has a wide band gap of 3.4 electron volts, a mobility of holes and electrons is tight. Its resistivity depends of the degree of doping and about the crystal quality. So the purpose of this project is this part, crystal quality. Next slide, please. The gallium nitride has two structures, two principal structures. The hexagonal, that is the most studied and the most stable. And another one is cubic. Cubic space is, we can find some works about that too. Next, please. Why we studied this material? This material has two principal properties that make it good for photoelectronics and the next generation. The one is that it could be used by high electrical potential, and the another one is has a good thermal performance. It's dissipate the heat very good. So these both properties make it that we can fabricate these materials, or we can fabricate some positives with high voltage and high current. So we have a high potential. This is comparative with silicon is better. Next, please. In the process for RF sputtering, for this material, gallium and nitrogen. In case of gallium, the gallium is a high atomic weight, so it is very difficult to deviate of the path. So in this case, gallium is not a problem. The problem could be the nitrogen, whose atomic mass make they easily deviate of the path, and that's why we have to maintain a rich concentration of nitrogen. The condition for this growing process was a pressure of 10 minus 5 torr, temperature of substrate 300 Celsius degrees. The growth time was 30 minutes, and in the project consisted in move or change the nitrogen flux rate in the mixed nitrogen argon inside the chamber from 0 to 100%. The next, please. And the results of BRX, we can see visually that the best results were for percents in close to the middle in percent, 50, and 70% were the best. And in the extremes, with the 100% and 90%, we have poor crystallinity, and in 0% of nitrogen, this was poor. In the table, we can see the results compare with the reference. In this case, 50 and 75%. The parameters of the cell was exactly 3.90 for the A, and 5.90 for the C axis in the hexagonal cell. Another situation, we notice that in the case of the 75%, we find some reflections corresponding to the gallium trioxide. In this case, naturally this oxide was formed out of the chamber. It is we need to improve the manage of these layers, and we need to down temperatures before open the chamber, and we need to better manage of the layers out of the chamber. The next, please. With the data of the DLX, we calculate the microstrain and the present density and the average grain size. The better results are for the 75% nitrogen with the 221 average grain size in nanometers. The microstrain was 4.44 for the microstrain to -3, and the location density was the lower 2.38. So in this case, it's clear the advantage of owning these layers at 75% of nitrogen. And the next please. We measure high resolution TM. In this case, with these images, we measure the interlayer distance for the 101 planes. In this case, both 50 and 75% nitrogen layers have close results compared with the reference. So in this case, we could say that both are good layers. Next, please. This is the Raman spectrums. In this case, really we don't get good spectrums. Maybe only the 75%. We have a good signal corresponding to the E2 high mode. In this material, we have 6 modes that we could obtain in Raman. In this case, the most presented in the most of the articles are E2 high and A1 low longitudinal optical mode. The E2 high correspond to the perpendicular movement or vibration of the nitrogen atoms in the z-axis, and the optical mode correspond to the vibration of all the cells along the z-axis. In this slide, please. Next slide, please. Okay, in this we can see the 2 modes. The ethos high is the vibration is transversal to the z-axis of the hexagonal cell, and the A1 longitudinal optical mode is in along the z-axis to the nitrogen atoms in one side, and the gallium atoms in the another side. This is very clear the modes that are more important or more reported for this material. Next, please. As we check in the before and the magic, the only one mode that we really could see in this spectrum is for the 75 nitrogen percent. In this case, is the E2 high mode is very clear and the only one defined. And others are in, we can say that they are present, but they are not well defined. Only this one is very, very, very well defined. And they are, it is at 567 centimeters minus 1. It corresponds with this kind of materials. It is supposed as the exactly all best value for this mode is 568 centimeters minus 1. So it's very, very close. The others really are part of the of be very well defined. Are very unclear. The table show all the modes. They are 8. Only 6 are we could find in Raman. All of maybe in another's in ER could find another. Okay, next please. As a conclusion, we could say that gallium nitride thin films were obtained by RF regeneration, changing the percentage of nitrogen flux in the organic nitrogen mixtures. X-ray diffractions and high-resolution TM and Raman measurement indicate that films with pure argon were amorphous and improved with the addition of nitrogen. The films with the best structural properties were obtained with 75% nitrogen flux, and the films obtained have the potential to manufacture some devices. Work that we could make about this project is improved structural properties of gallium nitride films. Some reference to the stress. Stress is high. We have to reduce this stress and the dislocations density. Measure the electrical and optical properties of deposited films. Apply deposited films to devices such as diodes and sensors. Okay, next please. Okay, some references. User. And next please. Okay, thanks for your attention, and you have some questions.
Thank you, Jorge, for your presentation. We have time for some questions. Does anyone have a question? Please, Doctor. There we go.
Hello, Jorge. This is Yasuhiro Matsumoto from solid-state electronics section here in electrical engineering in the staff. Thank you for your presentation. In your conclusion, you are mentioning that you obtain a gallium nitride by using a pure argon. I think it's not possible to grow gallium nitride in that condition. So you find out an amorphous phase. But could you explain again this conclusion?
This result, no? As a result of these experimentations, we noticed that with only argon, we couldn't find a crystal quality In this case, we with only argon, the layers were amorphous, and in the another case with only nitrogen were poor crystallinity.
Okay, but you are using a sputtering, RF sputtering. Is okay? So you have a gallium substrate, and you are using argon. So if you are not introducing nitrogen, how you can get a gallium nitride in this case?
In this case, it was. I'm not sure the structure. We need to maybe check XPS or another atomic characterization. But without nitrogen, the structure is very poor. We think is gallium nitride. But I really not sure until we characterize by XPS or at least EDS.
Okay, I mean, because if you are not introducing a nitrogen, how is possible to get a nitrogen from the sputtering? That is my question. Okay, another is okay. You find out a hexagonal ursite structure. How polycrystalline is involved? So in a 10 image you show, it seems a fraction, so 20 nanometers, very small crystallines. So I don't know, what is the average, how to say, in this case, at a 75% of nitrogen, it seems also is like a polycrystalline. So could you comment about this?
Okay, and the first part, okay, I think I omit to say that the white the white to this case was uh, gallium nitride. So we have in the white this material. Okay, so maybe in the slide 6, I forget to say the white is not the gallium, is gallium nitride gallium.
There are no more questions for her. So we thank Jorge for his presentation. Next presentation is aluminum modified tin oxide nanostructure as carbon dioxide sensor, effect of physical properties on sensitivity. Presented by Pamela Trejo.
Good afternoon, everyone, and thank you for being here. My name is Pamela Trejo, and I'm from Technological Monterrey. And our research is titled Aluminum Modified Thin Oxide Nanostructures as Carbon Dioxide Sensors, Effect of Physical Properties on Sensitivity. This research explores how aluminum doping on, in this case, tin oxides, with using green synthesis using lemon peel extract can improve our sensing properties of the tin oxide nanostructures. Okay, so we begin with some introduction. We know that dioxide carbon is a green, is a key green gas that is in the atmosphere, and also is a air hazard and air quality indicator that involves all the environmental properties and this environmental harmful. In this case, also the tin oxide is an inside semiconductor. In this case, we use for the high stability, also because it's an inside semiconductor,
and because it has relevant properties. And we use aluminum doping to increase the properties of the tin oxide nanostructure because aluminum doping has optical properties also increase the oxygen vacancies of the nanoparticles, and it has structural changes and responsive problems. Also, in this case, we use a gas sensor. In our research, the gas sensor is important because we know that in our environmental, it has a lot of problems and a lot of trouble of the pollution. So it has a high sensitivity, and also we use a green synthesis because we know that our planet nowadays is with pollution, and in this case we use lemon peel extract. So in the experimental part, to begin with the lemon extract preparation, we prepared a 6% solution with citrus powder was prepared, and then was constant stirring about for 2 hours, then heating for 1 hour at 60 degrees, and then only we filtrate the extract to have only the lemon peel extract. Then to synthesize the aluminum doping tin oxide nanoparticles, we prepare the solution. Then it has a constant stirring for 1 hour, sorry, and then has a water bath, then centrifugate, and then a heat treatment. In this statement, it has a temperature of 700 degrees that it helps us to have some porous nanoparticles and more morphological structure. Then for the preparation of our films for the sensor, we mix and stir the tin nanoparticles with the ethylene glycol, and then we place on a plate and layer with solution at 400 degrees. Then we have the thermal treatment of the fields. Then we have the Fourier transform infrared spectroscopy. In this case, the lemon peel extract, it has a blue line in this case. We see that it has carbon and hydrogen bonds and also carbon and oxygen bonds in this case, the flavonoids and essential oils in the lemon extract. Then in the line, it has a color red. It is the lemon extract, and it has the significance of the oxygen and hydrogen bonds, and then the hydroxyl bonds also. It means that it has the phenolic compounds of the lemon extract, and also the pectin is observed. Finally, in the black line, we see the nanoparticles, and we see a characteristics of the tin oxide, and the tin oxide tin bands confirm the structure of the tin oxide nanoparticles with aluminum. So this characterization helps us to confirm the interaction of the organic compounds of the lemon extract and the aluminum with the tin oxide nanostructures. Then we have the X-ray diffraction, that it means that our crystalline size was about 60.4 nanometers. In this case, our image means that it has the comparison of the tin oxide nanostructures and only the pure tin oxide. And this means that decrease of the interplanar distance due to an increase in the Pratt angle. And also in the principal peaks, we know that it has a 0.2 degrees to the right. So it only it means that it was a verification of the tin oxide nanoparticles formation. Then in this slide, we present the dynamic light scattering, the DLX, that confirms the predominant size population of the nanoparticles. It has two sizes of 310 and 361 nanometers, with an average particle size of 314 nanometers, sorry, and a standard deviation of 30.5 nanometers. This suggests that it has a binomial size distribution and also an effective world control because it has only two predominant sizes of the nanoparticles. Then, the process of particle growth, the divalent tin and the trivalent ions of the aluminum increasing the ionic dissociation, because when we mix our lemon extract, it begins to grow small pores, and then in the ionic dissociation, it increases with large pores, and then with the acid-base precipitation, it has a crystallite size, and then after the thermal dehydration of our nanoparticles, it has the particles grains. That it means that it has a good size. So it means that the aluminum, so with the nanoparticles, it's developed. So causes of the irregular growth are uneven dopant of trivalent aluminum distribution, also local concentration gradients, and also it depends on the pH variations. Also, we have the scanning electron microscopy to see our irregular morphology and high porosity of our fields. And also it has a porous structure. That the porous structure is important because it's more efficiently in our gas sensor, in this case the carbon dioxide, because it enters to the porosity and it has like a good diffusion and also accommodates with various gas sizes. This is formed by thermal removal organics and partial evaporation. And also, this helps us to loosen performance to more active slides, faster response, and also a high recovery time. In this case, we also see the energy dispersing spectroscopy. That it means that the strong peaks of the tin and the oxygen confirm the thin oxide nanostructures, and also including in our tin. And also, we know that in our structure it has oxygen, aluminum, and also tin. But also we detect a minor of carbon and a minor of sodium, because maybe the contamination or residual impurities. Also, this is like oxygen excess due to the substrate and adsorbed species. And the most important thing here is the gas sensing performance, because we see in the graphs that our sensor is like a switch-like behavior, because it has a consistent that of a 9-type semiconductor and interacting with an oxidizing gases. Also, we know that in this case, we could prove that our sensor saturation, the limit was of 100 parts per million, and it's the maximum detection limit. So we know that in our gas sensing, the most important part here is the sensor saturation at 100 parts per million at 300 degrees. And it also depends of the stability of the selectivity. And in this case, we know that our fast sensor responds with only 20 to 40 seconds. And also, it has a longer but relatively quick recovery times. And in this part here was the sensing mechanism of the carbon dioxide in our field. First, the oxygen of our tin oxide, it creates oxygen vacancies with energy, like I don't know how to explain it, but it abandoned the electrons. So then it would drop the electrons to introduce the carbon dioxide sensors, and it also the oxygen, that is the gas. We have the electron, and then the oxygen is absorbed, and then they form a surface with depletion layers that it improve our gas sensing properties. So in conclusion, our gas sensing was successfully with the lemon peel extract, because it has a linearity, a good sensitivity, a good selectivity and response time, and also the incorporation of the 4 weight% of aluminum that is mentioned before, promote the formation of the oxygen vacancies induced per morphology and improve the sensor performance of 300 degrees with a fast response and good linearity. And this has the applications of the using in the hospitals in public transport, because we know that it can like measure the concentration of carbon dioxide in a room. So thank you for your attention.
Thank you. We have time for question. Yes, please.
Thank you so much for your presentation. It was very nice. Can you please go to slide number 3, please? Here you are using different kind of ratios, right? Like 6% ratio of your lemon extract or your citrus extract.
Yeah.
Which ratio, which ratio for you was good to obtain your material? Like, what was the ratio of your extract and the salt that you're using, or the chemical compounds that you're using for obtaining your material? You used one part, like 1:2 ratio, 2:2 ratio of extract and chemical compounds, or which kind of ratio was perfect in your case in this study?
Okay, the lemon extract, we only the peels of the lemon.
Okay.
We use the 6% of concentration of lemon extract, and sorry.
It's okay, it's okay.
Yeah.
Relax, no problem. So, with the concentration of 4 weight% of lemon extract, you are obtaining the material. But what if we are using 2% of lemon extract? If we can reduce the amount of lemon extract, then we can eliminate the other phytochemicals. There are a lot of phytochemicals in other phytochemicals.
We know that the flavonoids and the pectin of lemon is an agent of it has agents properties to increase and increment the sensitivity and response time. So in this case, we also use tin chloride and tin aluminum to useful in the synthesis of aluminum and including the lemon extract.
Okay. And in the slide number 6, please. Yes. Here, you have performed the DLS scattering for the particle size distribution, right? And what about the stability or the zeta potential of the material? Do you know? Like if the particle was stable after 1 month. For example, I've synthesized one material here, and now the stability is like good. It's near to the range. But after 1 month, the particles are getting agglomerated or something like that.
No, we have not enough time to introduce after 1 month, after 2 months to check and to analyze the size of the nanoparticles after time level. So it is like a feature improvement in our research.
No, actually, you have mentioned here that minimal agglomeration, but minimal agglomeration, like you have said that you have done only 1 or twice the study, not after a lot of time, So agglomeration cannot be justified just with one time. You have to perform the stability again and again for 1 month of moments. But thank you so much. It was very nice. Thank you.
Another question,
I have a question.
please.
So there were used several characterization techniques in this study. I just want to know, in your opinion, which one of them was the most difficult to perform?
In this case, the most difficult was the gas sensing performance, because in our school it has like a in mecanismo casero.
Homemade mechanisms.
So in this case was the most like difficult part because also we have problems with the measure of the carbon dioxide, and it also depends of the gas. Also, we can do like with acetone in other cases. So in this case, I think that was very sensitive.
Thank you so much.
Pamela, what is the importance of seat vacancy with the performance of the passenger?
Because the gas can enter to the pores and absorb the structure, so it can like yeah, it has a pore when the gas enters and it's absorbed and also vibrate to like keep up a la energía para yes with the characterization to increment the sensitivity of the gas.
It's like a chemical,
Yes.
electrical or chemical.
Yes.
No, actually. It's not the word, the right word, but it's like active, it's a chemical electrical point. Vacancy is an electrical and chemical heat point to absorb the gas. Yes. Okay. Thank you, Pamela. Yeah, yeah, no, please, Dr.
Thank you for your presentation. So you are concluding that eco-friendly octane in oxide has a better sensitivity for a sensor. Did you compare with some conventional method to obtain tin oxide? Why you can mention confident that this eco-friendly method is better?
Sensor, like so it will help us in another future, but we don't
So
compare.
you may have to compare with
Yes.
other method. Okay.
So we thank to Pamela for the presentation. So the last presentation is so ídolo carboxol wafer thermal sample molecules as whole selective electrode in first hit solar set presented by Jose Guadalupe Sanchez.
Okay. Good afternoon, everyone. Thank you for coming. I just before to start my presentation, I want to comment is I carried out this work last year when I was working as a doctoral researcher in the Institute of Chemical Research of Catalonia in Spain, and we did this work in collaboration with the University of Murcia, also in Spain. Okay. Okay. Okay, this is the outline of the presentation. First, I'm going to give you a small introduction about the perovskite solar cell. Then I'm going to start to explain a bit the self-assembled monolayers, the SAMs. And then I will explain the fabrication of the solar cells. And I'm going to show you the results and the discussions of this. Okay. And finally, I'm going to conclude and give you some final ideas. For the introduction, well, the perovskite solar cell has attracted a lot of interest in the last years because they are kind of semiconductors, or they are devices with a high efficient, and now they are more stable every day. So that's why the people is searching more, not only in the typical or the standard photovoltaic model, they also try to buy in different applications. That's why the interest in the perovskite solar cells is increasing day by day. And this is the most typical chart of the efficiency evolution of the efficiency evolution of the solar cell. All the types of the solar cell are included here. And we have here more or less, you cannot see because it's a little bit small, the perovskite solar cells. That's why I prepared this plot just to show you the comparison of the evolution of the efficiency of the perovskite solar cells with the most typical or the most famous solar cells made with the silicon. As you can see, the increase in the efficiency is very fast. So in the span of I don't know, maybe 10 years, they increase a lot the efficiency. This evolution of the efficiency is mainly related with the structure of the devices. They start with these two structures, then the structure, the people start to change the structure of the devices. So finally, in the 5 years or more or less, we have these two structures that are the most efficient in these days. We have first the NIP planar, in which we have this organic molecule. This molecule, this spiral octet, is used for the whole transporting layer. In this structure, we have this molecule on the top of the perovskite, and then with this molecule, we can say it's the most efficient up to now. But there is one problem with this molecule: is we need to dope the material to increase the whole mobility, and in this way we improve the efficiency of the device. And then the people try to replace this material, so that's why they develop the inverter structure. Now we have on the bottom of the perovskite, we have the whole transporting layer, and then the people start to try to develop more material. Then the people found this polymer, another organic material, the PTAA, and it's working very well. This is up to, I don't know, last 2 years, it was the most efficient material for the perovskite solar cell. But the problem with this material is it's very hydrophobic. So the problem is when you try to deposit the perovskite film, you will have not the reproducibility very well. So that's why the people start to try to develop more and more materials in order to replace this molecule. And that's why the people around 5 years ago, maybe, I don't remember very well, they developed or they try to use the self-assembled molecules, the SAMs. And here I'm going to explain you what is a SAM. The SAM we can divide in 3 parts. The first part is the anchoring group of the molecule. I'm sorry, this is another organic material. The first part is the anchoring group. This part is going to attach to the substrate. In the substrate, we have metal oxide, metals, or other kind of semiconductors. Then we have the spacer group, which is only, how to say, it balances the charge in the molecules. And finally, we have the functional group, which is going to interact directly with the perovskite. So for this kind of material, people investigate a lot. So they change they have different groups, different in the top mainly, to have a better performance of the devices. So here is only the evolution of the perovskite solar cell using the SAMs as a whole transporting material. And this is the benchmark of the SAMs in the perovskite solar cell, the 2-pack molecule, and then they have the methoxy 2-pack. And then I try to show you this molecule because this molecule was synthesized in my last group when I was working in the ICQ. And then starting from here, the people start to work more and more in the design of novel SAMs. And as you can see here, one of the most important group is the carbazole. The people focus most on the carbazole because it's the most efficient material up to now. And here I show you how to say how it's easier to prepare these molecules. First with the 2-pack, and we start with the carbazole group, and then with very simple chemical reactions, we can obtain more or less the same molecule, but with changing the R. The functional groups. Okay, so in this case, we have also the fluxine. Is again we start more or less. If you can observe here, we have the carbazole group, but in this case, there are like three carbazole groups, but they are sharing in the center one benzene. That's why. Sorry. Excuse me. Screen is turned off. No.
We have time. We have time. We have time. Also.
Yeah. Don't worry, something that. Okay, sorry for that. Then, okay, so here I show you again. They are not the most important SAMs now, but this is I mean, the 2-pack and the methoxy 2-pack, the trypsin, this is also efficient molecule. And then again, I want to just show you the structure of the EADR03 because it's the molecule I use as the reference because it wasn't synthesized in the group in which I was working. So we have it there. We don't need to share. Actually, this molecule is commercial. And as I explained you, the carbazole group is one of the most important now. So that's why in the University of Murcia, the people, they think we have the carbazole group, and then the people have used 3 carbazole group. So that's why they're using the indocarbazole, in which it's like a 2 carbazole groups. So they prepare these 2 molecules. Actually, they prepare more than 2. But for this presentation, I want to be a little bit faster, so that's why I choose the 2 more efficient. And this is just to show you how is when we deposit the SAM we have in the same imagine. Well, this is the cross section of the device. We have the ITO, and then we have the perovskite. As I commented before, we have the SAM below the perovskite. And then, as you can see, this is a small line. And when we have a zoom, we can measure the thickness of this layer, and it's around 2 nanometers. So with this one we demonstrate, we can deposit a monolayer. That is the main idea of the SAMs. And then here there is we can observe the effects of the SAM on the perovskite. First, at the beginning here, we observe there are kind of 2 different crystallinity of the perovskite. Here we have small crystals, and we have I mean, the crystallinity in the bottom is higher than on the top. Okay. And then we also investigate the effects in the morphology of the crystals and of the perovskite using the SAMs. We have first the contact angle. First, when we have only the ITO, the contact angle is very low, and then when we have the SAM, the 2 nanometer SAM, we see the thickness, the contact angle increase. So later we measure again the top imaging with the FSM. From here we observe the crystal size of the perovskite increase when we have the SAMs on the bottom. One of these explanation, because we observe here we have a little bit higher crystal size when we compare the SAM without the methoxy group, and then we have the same SAM, but then with methoxy group, there is a little bit higher crystal size. And this can explain because the methoxy group can have, let's say, reduce the nucleation density. So we have the grains grow a little bit bigger. And then we demonstrate just small change in the molecule can affect the performance in the perovskite. And also we measure the photoluminescence. In this one is in this kind of analysis for the perovskite solar cells, we want to know how the SAMs will improve the extraction of the charge from the perovskite. Typically, when we have a whole transport layer in the photoluminescence, we can observe that the photoluminescence decrease in comparison with the perovskite field. This phenomena is called the quenching, and it means you have extracting the charge from the perovskite. But in this case, we have the opposite. We have higher photoluminescence. In this case, the phenomena is different. The phenomena is a passivation. That means the perovskite can reduce the defect in the surface of the perovskite, and then the charge is going to let's say I forgot. They are less recombination in the interface between the SAM and the perovskite. And also, we measure the time resolved photoluminescence. In this case, we observe the decay of the photoluminescence over the time. And for the case of the SAM, without the metoxy group, we observe we have a longer lifetime. That means the longer lifetimes it represents the first, we demonstrate there is a passivation from the SAMs. And second, we have a lower recombination in the interface between the SAM and the perovskite. And finally, we prepare perovskite devices. We use different SAMs on the bottom. The perovskite, for the perovskite, we use the typical triple cation pharma. And then we use PCBM and BCP. And finally, we evaporate silver as the top contact. From the JV cube, we observe when we measure in the forward and the reverse, we don't have hysteresis. Well, we have, but it's very, very small in comparison with the others perovskite solar cells using, for example, the spironolactone. That with the spironolactone is typical you have kind of hysteresis. And the other is the devices have efficiency over 20%. That is good in the perovskite solar cells. And from here, the samples using the SAMs without the methoxy group, they show the highest efficiency. Here, I just want to show you there is in theory, when we have the HOMO level of the whole transport layer deeper, we will obtain a higher value of the VOC. Sometimes this is not a demonstrate because we have more problem, but in this case, we have this. And then we also want to investigate more in the recombination in the perovskite solar cell. So we measure the dependence of the VOC on the line intensity. In this way, we measure the JV curves with different line intensity, then we extract the VOC values, and then after fitting with this formula, we can extract the ideality factor. So in principle, the ideality factor should be between 1 and 2. The ideal should be more to the 1. And then this represents you don't have any kind of recombination. But in this case, we have values around 1.2 for all of them. They are very similar. But we observe for the sample with the SAM without the electrolytic group, we have the lowest values. This means we have the lower trap assist recombination. And also to demonstrate or investigate even more how the SAMs can reduce their recombination in the device, we measure the transient photovoltage. And in this one, we observe the VOC decay over the time. And then similar to the photoluminescence, time resolved photoluminescence, the longer time represents a longer carrier lifetime. That means the charge, the lifetime of the charge is longer, and then they recombine not too fast in comparison with the In the case of the SAMs without the metoxy, we have a longer lifetime. That means the charge cannot recombine too fast in comparison with the SAMs with the metoxy SAM, with the metoxy. Finally, we prepare the space charge limited current method to calculate the hole mobility in the whole device and also the drum density. First, for the drum density, we observe we have more or less the same values. That means there is not a huge difference between these two SAMs. But for the case of the hole mobility in the whole device, we observe there is a higher hole mobility in the SAMs without the metoxy. This one can help us to understand why we obtain a higher current in the devices with this SAM, and also why we have a higher efficiency. And finally, we measure the stability of these devices. Actually, here, these two devices show more or less the same stability. In this case, for the SAMs without the metoxy, we observe there is a strange behavior in the around 1,000 minutes, but more or less they have the same stability. But most important here is to demonstrate they have a similar stability than the reference with the SAM. This SAM report in optimal conditions report very high stability of about I don't remember, maybe 1 month. So this is the main idea from this plot. Finally, the conclusion of this work, the SAMs without the metoxy exhibit the highest efficiency. The problem with the metoxy SAM is the metoxy groups reduce the interfacial electronic between the SAM and between the ITO and the perovskite. The SAM without the metoxy shows the better energy alignment and more efficient hole extraction than the perovskite. And this one have the carrier lifetime is improved in the SAMs without the metoxy. And finally, the SAMs without the metoxy demonstrates superior advantage, and we don't have any kind of substitution in the Canvas algorithm. I want to acknowledge my ex-group in the Palomares in ICQ, and also the group from the University of Murcia that they have synthesized the SAMs, and of course the funding support. Finally, I want to thank you all of you for your attention.
Thank you for the presentation. We have time for questions.
Please. Thank you for the presentation.
Yeah.
I am wondering about the optimization characterization.
Yeah.
So,
Okay, you will here, please.
So with that technique, we can measure or give us an idea about our defects interface.
Yeah.
It can show us that. So how can I do that technique in my link films? How do you prepare your sample? Yeah.
Okay. First, typically you use a glass, and then you deposit first only the perovskite because it's the reference, and then you deposit your electron or pore transporting material. And then you measure directly with the photoluminescence. I don't know I don't remember the name of the equipment to measure photoluminescence. I forgot. But you measure directly. And then sometimes the people use a kind of protection because the perovskite is in the air. So the people use PMMA. In this case, I use ITO because sometimes the measurement is quite takes a lot of time. So when we have the ITO extract the charge directly from the perovskite. That's why we have a very small And then when we have the sun, this value increases. But yes, but the question is like this: there's glass or IPO, and then the perovskite, and then the materials we want to analyze. Next, you're welcome. Ivan, I think it's fluorimeter. Fluorimeter, the name for the system to measure the photoluminescence.
Thanks.
Please, Dr. Thanks for your presentation. Could you show again the photovoltaic decay? I have some doubt. Okay.
Yeah.
Yes. In case of that is I guess yes, it's
Is the reference?
it's the reference.
Yeah.
So I think that should be the best
Yeah,
material.
exactly. Yeah.
So why is not how to say reflected that condition for
Yeah.
efficiency?
Yeah, I don't remember right now, but it's depending on the 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 recombination is also the extraction. In this one, I didn't show, but I think we measure the fold mobility. Yeah. No, this one is not. So, yeah, here I didn't show you, but I remember we measured also the fold mobility for the reference, and for this sum is still high. I mean, the fold mobility with the other sum, the reference, is a little bit higher than this one, but not much. And then we have the hypothesis, the recombination is less than the other one in the reference, but it's not only the recombination, but it's also the extraction from the perovskite. So that's one the conclusion we have in that moment. The sum without the metoxic can extract a little bit better. Because here you see the current is a little bit lower, and then also you have a little bit lower fill factor. That should be, you have less recombination, you should have a little bit higher. But yeah, there was many let's say no problem issues we found, but right now I don't remember. But we have reported here in this paper, but honestly I forgot right now.
Because the conventional the field factor is still lower brackets.
Yeah.
No, yeah. Great. Okay, thank you. You're welcome.
Another question, please?
Yeah, thank you. How important are the ambiental condition or the glow box condition for high quality perovskite cells?
Well, honestly, I was working all the time on their nitrogen condition because these materials are quite sensible to the humidity and the oxygen. But I know they are kind of when you modify the composition of the perovskite, you can work until 30% of humidity in the air. But yes, it's when you work, of course, in the nitrogen condition, you will obtain a better quality in the perovskite morphology.
Finally, explain the composition of cesium on the.
Oh no, sorry, it's 0.5. My bad. It's 0.5 because this one, all of this is 95.
Okay, thank you.
Any question? There are no more questions, so we thank to Jose for this presentation. Okay, with this, we conclude this session of the Nanomaterials and application. Thank you so much for your attendance and participation. And I would like to thank the organizer of CCA too. Thank you.